to basic advanced math. You know what time it is? It's time to do math. We're still in the Calculus BC or Calculus 2 section. And what we're going to be talking about today is arc lengths and the work to fill tanks. We're going to start off with arc lengths. We're going to get straight into going over it. So basically what an arc length is, let's say you got a grid, you have right here, you have a line, right here you have a line. In between these two lines, you have an arc. This is called an arc. You want to know what the length of this line in between these 2 points are here. These lines are imaginary. You want to know what the length of this arc is in between x1 and x2. Today we're going to be going over how to do that. So basically, the simple formula is, for arc length, it equals the integral from x1 to x2, because we're starting here, going here. It is going to be the square root of 1 plus y prime squared dx. So what you're going to be given here is going to be the equation of y or x. It doesn't matter, because if you're given it in x, you can simply write it in terms of y and solve it. And we're going to have the 2 points, x and x squared, that we're going to be going to. So let me write down an example problem real quick. All right, we have our problem right here. And just out of this, we have everything we need to know to plug into this formula and get the answer. So it's very straightforward. What we're going to do is we're going to write down the formula and fill in the blanks, and we're going to go from there. So we write down the integral first, of course. What is the integral going from? From x1 to x2. We have the points, both points in the graph. You don't care about the y's because that doesn't matter. We're going for x's. Starting at the first x, which is 4, of course. Start right here, you get 4. Next x is 16. Simple. You got that down. All right, the square root. We have 1 plus y prime squared. If you don't know what y prime is, it's just the derivative of the y function. All we have to do, 1 plus y prime. I'm going to solve for y prime right here. The derivative of square root of x is simply 1/2 x to the negative 1/2. You can plug it into your calculator. You can do whatever you want, solve it, find a way to get y prime. That's not the most difficult thing. And then we plug that in and we square it because it's in the formula. Square on the dx. And we're done. We plug this into the calculator, or you can solve it if you would really want to solve it. I wouldn't solve that by hand. I'd plug it into the calculator. If you can't solve it by hand, go ahead. This extra practice is good. I'll draw a little graph real quick to show you exactly what this would look like. This is approximately what the graph would look like. So this equation right here is how you would find the length of that line right there in between 2 points. That's it. All right, guys. The next subject we're going to be talking about is work filling tanks. In my opinion, this is one of the most difficult subjects in all of calculus, at least calculus 2. You're probably going to have to do a good amount of work, honestly. But you can do it. You can figure it out, and you can become a master at figuring out how much work it takes to fill up the tanks. So let's get straight into it. Basically, what we have is we have a tank, say it's above ground or underground. It's going to be a certain distance from where you're starting at. We'll say this one's underground at the moment. We're going to be using a cylindrical tank just because you could do other shapes, but a cylinder is the most common one to use. So say you want to pump water downwards, you'll shoot it into the center of the tank. You want to know how much work it will take to fill this entire tank, or you can go from any point to any other point. The basic formula from this is going to be work. It equals the integral from A to B. Now work itself is force times distance, and force is going to be density times volume. We're getting into the physics here. This is not exactly 100% calculus. However, it's an integration of the two, and you've got to know this stuff. So we have the integral from A to B of density times distance times volume. It looks pretty easy right now, right? We're going to get to that. We're going to get to each of these separate steps. Density, that's going to be the easiest one. They're going to almost always give you the density of whatever you're filling with. It's the distance and the volume that you've got to solve for. So I'm going to write up a little equation, and we're going to dive into this, and we're going to kill it. All right. So I drew the little equation right here. We've got a tank that's 20 feet up from where you're pumping it from, 10 feet long, 6 feet in diameter. So we're going to start off this equation. We're going to fill in what we can and then solve for what we can't fill in immediately. And we're going to knock this thing out. So we've got the integral from blank to blank. We don't know where that is yet. We already have density. Say this is water. So water is going to be 62.4 pounds per foot. Foot per pound, either one. The density is 62.4. We're just given that. We're pretty much always going to be given that. And if not, you can solve for the substance given what you have. We're just going to do 62.4 because that's a pretty common one. Distance. What is the distance that we're pumping this gas? As you can see, when we fill up this tank, we are not filling it up 20 feet at all times because as the water gets higher, we're going to have to pump in water to a higher point. So the height that we are pumping it into is going to have to change as we go up and down. So the way that we're going to fill this up is we're going to fill it up in little tiny rectangles. Much like we did the volumes of revolution, we're going to have to solve this using an integral that takes a little tiny piece. We solve for the area of that or the volume of that, and then we stack them on top of each other, add them all together. So because this changes as we go up and down, there's going to be a variable in the formula for the distance. However, it's still not going to be difficult to find once we know what we're doing because we got this. So here's what we're going to do. We've got the distance. We've got 20 feet up plus, we're pumping it 20 feet up plus wherever we're at in this. So we're going to say say that the center is going to be 0, 0. My bad, guys. I accidentally misdrew this a little bit. We're actually going 20 feet from the bottom to the center of the tank. I could have done to the bottom of the barrel, but this is just so much easier to explain. So we're going 20 feet from the bottom to the center of the tank. Now we can find distance. Distance is not going to be 20 feet at all time, like I explained. We already know that. What is it going to be? Well, we can find out using just logical deduction that it is going to be y plus, if the center is 0, 0, it's going to be 20 plus y, whatever it is. Say we're at -3, the y is -3 at the very, very bottom, because this is 6. The lowest we'll get is -3, the highest we'll get is 3. So it's going to be 20 plus -3, 20 minus 3. We're filling it up 17 feet when we're here. That works at all places. So the distance formula is going to be 20 plus y. We can plug this in over here. All we need left is volume. This is going to be the toughest part. So let's get into the volume. All right, guys, volume. This is what we're going at. So the volume that we are finding is not actually the volume of the cylinder, because as we're changing every time we go up, we're actually finding the volume of this little rectangle that we're filling up, the rectangular prism. So we're going to draw that right here. You guys know I'm a terrible drawer, terrible artist. However, we need to find the volume of this rectangular prism going across. And then we are going to find the volume of each one, add them all together to an integral. You know how that goes. What is the volume of the rectangular prism? We know the volume of a rectangular prism is going to be length times width times base. So length times width times base. We have to fill in each of those. What is the length? We know the length is 10 feet. That's the easiest part. We're going to say the length is going backwards. So we know the volume is 10 times something. Now we need width and base. The dimensions are going to be this way and this way. We can easily tell that one of them, doesn't matter which one you describe it as, I'm going to call it base. One of them is going upwards. One of them is the y that we are changing every time we go up. So I'm going to call it base. You can call it width or base. It doesn't matter what order you do these in. But one of them is going to be dy, because every time we go upwards, we change the y. So then after this, we are going to get dy. What comes before dy? Well, that is the width. And this is probably the most difficult part of the entire thing, is trying to find the width of the volume that you're trying to solve for. So here's how you do it. Kind of difficult. You got to know what you're doing. We're gonna do it. So right here we have 0, 0. This is the point. We need to find the width. What is the width? It's right here. We know that. What is the measure of it? that's where we're going to use some geometry to figure out what we have. So what do we have? We have the radius is 3. We know this because it's 6 feet tall. So diameter is divided by 2 is the radius. That is 3. We'll go to this point. This line is 3. Now what is this line? That's all we need left. This line is going to be y. As you remember, wherever we are on the integral, we're going up and down in y. So we start at 0, 0. We could go down to minus 3. Right here would be 0 minus 3. Up here would be 0, 3. However, the distance that it travels up and down, that is y. That's what we're changing right here. And that's the last key to solve the theorem. My boy Pythagoras made this pretty easy for us to solve. All we have to do is plug it into the Pythagorean theorem, which is, of course, a squared plus b squared equals c squared. I'm not going to write that out, but we know that this right here, we'll call it x. X is going to equal the square root of, this is hypotenuse, these are the two bases, they form a right triangle. So x is going to equal the square root of 3 squared minus y squared, which is going to be the square root of 9 minus 3. However, that's just 1/2 of it. We multiply it by 2. So overall, we are going to get 2 times the square root of 9 minus y squared. And that's it. This is the formula for volume. Now we plug that in up here. We have 10 times the square root of 9 minus y squared, because that's what we got right here. And then this is where we get our final dy. We're so close to finishing this integral.